Okay, so it's the second time I'm teaching here. I gave a seminar last year, more or less on the history of game theory. Now it's another survey on no regret procedure. Okay, so this started a long time ago, like 70 years ago, and I will try to explain the main ideas. I'm not using this. Okay. So it's a survey on no regret procedure. I will recall the first initial framework, which is finite state, discrete time. There is a stochastic aspect, and there is some connection with games. And the second part will be on the deterministic extension to a continuous state, continuous time, and connection with online algorithm and convex optimization. If you have any questions, so please let me know. Okay, so the cornerstone. In game theory, it starts with Hannan and Blackwell, so it's go back to 55, 56. The name no regret is due to Hannan, and the proofs use tools introduced by Blackwell. So in statistics, there are related preoccupation with Vogt and Littlestone-Varmuth. In optimization, the algorithm related to this are due to Polyak, Nemirovsky, Nesterov, and then Korpeligiv, Popov, and so on. So in biology, there is connection with replicator dynamics due to Taylor and Juncker, and there are a lot of papers in operation research, especially in congestion, that are related to this area. So a notion of regret, it appears in Hannan, 57, and Blackwell in the game theoretical setup. And then you have plenty of names because it was a very active area, but it starts quite a long time after. Okay, you see there is like 40 years between the first Hannan and Blackwell, and then for a while it was not used, okay, and then it came back like 40 years, 30 years after. Okay, so this is a few names here, okay, and so these are some related books, okay? So this is game theory and no regret, okay? Okay? So these are kind of quite references, okay? And then the similar tools and property in statistics in the learning community, okay? So it starts with Vogt and then Tom Cover, Littlestone-Varmuth, Freud and Shapiro, and so on. So you see, it's a huge literature, okay? But here, these are the two main branches, game theory and statistics, okay? Then I will discuss the connection with optimization later on. So part one is no regret. So this is the initial formulation. It will be discrete time, discrete framework, and some stochastic aspect. So online algorithm and no regret. So you have an agent in discrete time facing an unknown environment. At each stage, you choose a point k in a finite set. So at stage n, you choose k in a finite set. Then you observe a reward vector, so a vector with k component. And the outcome is the component you were choosing. So first you choose the component, then you observe a vector, and the result is the component of the vector you were choosing. So it's adversarial framework, meaning that there is no assumption on the reward process. Okay? It's as if you were facing an adversary who will choose a sequence of outcomes. Okay? So at each stage, you choose as a function of the past history. Past history is your choice at stage 1, then you observe the vector, then the choice at stage 2, you observe the vector, and this was yesterday, your choice, and the vector yesterday, and today you choose a new component Kn. Okay, so a strategy is a map, as usual, from history to choice, okay? And you will be allowed to make a choice at random, because otherwise there is a deterministic process and your behavior is predictable, and this is bad in all this framework. Okay? So the point is how you evaluate this procedure, and the procedure will be evaluated through the external regret. So the external regret is defined through the regret. Regret is you are given a choice k and a vector u. The regret is the difference between the vector and the component you were choosing. And then the evaluation of the procedure, given a strategy sigma, will be defined through the sequence of regret. So at stage n, you were choosing kn, the vector was un, and the regret will be rn, which is r and u. So it's basically the vector minus the component you were choosing. So if you are choosing the best component, the regret will be negative everywhere. If you are choosing the worst component, the regret will be positive, but you don't know the component before. You choose first the component, and then you observe the vector. Okay? So the average vector is, as usual, denoted by Rn bar, okay, and the average. Okay? So what you do is you compare the average payoff to the average payoff corresponding to the choice of a constant component. Okay? So every day you choose different component, and you compare to somebody who will choosing every day the same components. So this concept was introduced by Anand. This is a no-regret component, and it was developed in particular by Fullenberg, Levine, Foster, Vora, and a lot of other people. So this is a picture. Here you have the set K. This is finite, okay, and you choose what component. This is time. It's finite. Every day you see there is a vector U1. So at stage 1, you choose the component K1, then you observe the vector U1. And this is your outcome. Stage 2, you first choose the component K2, then you observe the vector U2. And this is your sequence of choice. Okay? Given a sequence of choice, you have a sequence of reward. This is what you get at stage 1. You get the K1 component of the vector U1. Stage 2, you get the K2 component of the vector U2. Okay? Every day you choose a component, then you observe the vector. And the outcome is the component you were choosing of the vector that appeared. Clear? So this is the trajectory you choose, and the payoff is on this trajectory. And you compare this payoff to a constant payoff. You compare to this guy who was choosing every day the same component. Okay? And what you want is you are better than this guy. But for every L. So no regret means that on the average, on the path you were choosing, you are better than every constant path. You are beating all the players who are choosing the same component. Okay? So if you have a procedure that has this property, you said you have no regret. Okay? You are better than any constant. Clear? This is the no regret property. So,
have regret to having me as PhD
sorry?
student? Did you have regret to having me as PhD student?
So Bader is laughing. Bader said, well, should I say the truth or, okay, should I be polite? Okay, you want me to be polite? I will be polite. Okay, next question. So a strategy satisfies what they call external consistency or generates no external regret if for every process, so you don't know anything about this process, you choose the component and you observe, okay? So for every process, this is the component, the guy who was choosing every day, K, this is what you got. And on the average, this is a small o of n. So if you divide by n and you let n goes to infinity, on the average, you are beating all the constant choices, okay? So it means that the average payoff on the path is asymptotically greater than on any horizontal line. The average payoff on the path you were generating is greater than any constant payoff. Clear? This is the no-regret property. Okay? And it has to be true for every UN. You don't know anything about the process. Okay? And what we are going to show is that this exists.
You can give an interpretation with experts, perhaps?
It's good that you are here. Okay? Because otherwise there will be no question. I remember this guy, 35 years ago, he was lying on my desk saying, well, we are going to make a good PhD together. That was a lot of fun. Okay, so one example, one interpretation, I like it, is due to Tom Cover. So it was a guy in statistics in Berkeley that I was quoting, which has something to do with finance. So this is for Bader. You have finitely many banks. So K is a set of financial institutions, and every day you choose one of them. Okay? And then there is a reward for institution 1, institution. So there is, at stage 1, at stage 1, there is the reward U1, and this is for institution 1, this is for institution 2, and so on and so forth. Okay? So each day you first choose an institution, then you see the reward. Okay? And then you get the reward corresponding to the institution you were choosing. Okay? And what is the no regret condition? It means that on the average, you are beating all the guy who is choosing every day the same institution. Okay? Meaning that you realize the convex hull of all the U. Okay? Yes? By changing banks every day, you beat all the guys who are choosing the same bank. Okay? Without having any information about the rewards. Okay? You adjust. You look at the history, you adjust, and on the average, you will be better than all people choosing the same financial institution. Okay? So this exists. And then you have even a property about speed of convergence and things like this. We'll see that later on. Yes?
Is the payoff known for a person who chooses the same who makes the same choice every day, similar choices? The payoff already known in the graph you've shown earlier.
No, the guy is in the same position than you, okay? But he's choosing every day, and every day he will discover what is the vector u, and he will get the component L, if he's choosing L, okay? But he's not changing, okay? Yes? Again, if you look at this, so if here you have a sequence of vectors, you don't know anything about the vector, okay? Tomorrow, you are here, you don't know what will be un plus 1. And what you want is to generate a trajectory such that, on the average, on this trajectory, you are better than every horizontal line. Okay? And if you think about it...
No, but in the horizontal line, the payoffs of every day are not constant. They are changing.
You are looking on this line on the average. Okay?
You know, basically, you know only that they are bounded between A and B.
If you think about it, you will realize that the same proof will show that it's true for every finite set of paths. Okay, the fact that it's constant is not important, but given any finite set of paths, you will be better. Okay? And these are one of the extensions. Good. Now, internal regret, so it's a bit more specific. Okay? Internal regret now, it's defined not by a vector, by a matrix. And the GL component of the matrix, so it's still a function of your choice K and of the vector U, except that it operates only on the line L. So, line K. Okay, so basically the matrix, if you choose the column K, okay, then all the other columns will be 0, and on this column you have the previous vector, meaning U minus the component you are choosing. Okay? So the evaluation is given by a matrix where you have 0 if K is different from K1, and otherwise you have this vector here. And the average internal matrix is this. Okay. So what you do is that you comparison for each component of the average payoff obtained on the dates where K was chosen, corresponding to the average payoff for an alternative choice. So this was introduced by Foster and Vora, and Fudenberg and Levine later on. Okay, this notion of internal regret was not explicit in Annan or Blackwell, and the picture is the following. Again, you are choosing every day a component, and then there is a sequence of vectors. This is the choice that you were generating. And what you do is you fix K. You look at the date you were choosing K. And on this date, you were comparing to another guy who was choosing L. Okay? So you are not looking at the average of your payoff, but for every specific k, you look at the average payoff on the date where you were choosing k. So on the date where you were choosing k, it was better than every other choice. And this is true for every k. Okay? So in the previous case, you were looking at the average. On the average, you are better than any constant. Now it's more sophisticated. It says that whatever being your choice, if the number of times you were choosing k is not vanishing, then on the average, when you were choosing k, on this very date where you were choosing k, it was better than any other choice. Okay? So this is called internal consistency. Obviously, if you are better on this date and for every k than any constant, it implies the previous one, but it's more sophisticated. This is called internal consistency. And you have the same definition here. A strategy satisfies internal consistency if or exhibit no internal regret, if for every process, now these are positive part of matrices, okay, and you want that all component goes to 0. So it's comparison with horizontal line on each section of the trajectory. Okay? So think of you are predicting the temperature, saying that it will be 0 degree, 10 degree, 20, or so on and so forth, okay? So on the date you were predicting that the weather will be 15, you were right. It was better than any other choice, okay? So this is very much related to another notion in statistics, which is called calibrating. Calibrating, so this is prediction of some random event, and to be calibrated means that when you make some specification or prediction on this date, on the average, your prediction was the best one. If you want to see connection between internal regret and calibrating, there's this paper by Vianney-Perchet, who is very good. Okay, so now you have these two notions, external regret, internal regret. And now there are several proofs of existence of strategy satisfying this property. Here we use approachability, following the proof introduced by Sergio Hart and Andrew Mascolel. And approachability. So all this is due to Blackwell. And Blackwell is a two-person zero-sum game. The point is that it's defined by a matrix, but the outcome is not a number, it's a vector. So you have a matrix, let's say, one player will choose a point I, the other player will choose a point J, and then the outcome is this, but this is not in the number, this is a point in RK. Okay? And then you have a repeated game in discrete time, so every day you choose a line, the other choose a column, this generates an outcome, so you have a sequence of points in RK, and you look at the average, and then the approachability is, so this is a description of the game. It's the fact that you have delta here means that you choose at random. Then you have couple GC. This is the history. A strategy is, as usual, a map from history to random choices. And then this generates a path. And given a set C is approachable by player one if for every epsilon there exists a strategy, namely a way of choosing the point I at random, such that the distance, dn is the distance between the average of the result and the set C, okay? So you want that the expectation of the distance will go to 0. More precisely, that for every epsilon, there exists capital N, such that the expectation of the distance will be smaller than n. Okay? So it means that a set is approachable if there is a way. So this is Gn bar. You look, this is a random variable. You look at the distance from Gn bar to this set C, and then after some stage, capital N, you know that you are at a distance that is less than epsilon. So this is the notion of approachability. So what will be the use of approachability here? But remember that you have this set K of choices, and you want to beat. I will do it for the case of external regret. To prove that you are better than any fixed choice means that you have a vector payoff, okay? And what you want is that all components will be eventually negative, so you want to approach this set C, which is the negative hortant. Okay? So to prove this property of no regret means that you will use the approachability of Blackwell in the framework where the set C has this very specific form, which is the hortant. Okay? And what I will use from Blackwell is the following result. It's a sufficient condition, and it says that a closed set is a B set. It has this property. Namely, if you are not in the set, you look at the closest point, and there is a way to generate a payoff on the other way. So what is approachability here? You have a set C. So assume that you have a set C, and a sufficient condition for approachability will be the following. If you are not in the set, you look at the closest point, you look at a hyperplane which is orthogonal, and you want that for every Z, there is a way to generate something which is on the other side of this hyperplane. Okay? So for every Z, there is a way to generate something, okay, which is on the other side. So this is what is called a B set when you have this property. And one of the main results of Blackwell is this property. If you have a B set, then this B set is approachable by the player, meaning that there is a way of playing every day such that the distance to this set goes to 0. Okay? And this is what we will use in the framework of no regret. Okay? And this is the set C. So it's not necessarily convex, whatever. This is a point which is not in the set. If you are in the set, you can do whatever you want. You take a point which is not in the set, a closest point, a line which is perpendicular, and it means that for every Z, you can generate something. You know that the set of expected outcomes under your strategy will be on the other side. Okay, so you have this property that for every Z, if you look at a closest point, then you have this property here, scalar product which is negative, okay, which is written here. So it's Z outside, W, which is the closest point, U, which is the outcome tomorrow, but you don't know. So you look at the expected payoff tomorrow, and you have this property. So this is the fundamental property of Blackwell. And the existence of strategy satisfying external consistency, we prove the existence by showing that the negative hortant will be a set C, and that there is a strategy satisfying this. And in fact, here it will be very elementary because it's related to this. Okay, so you have to understand this is the geometry property explaining that you have this. Okay, so R, remember it's a regret. This is a vector. This is K, but you will choose, this is a component, but you will choose the component at random. Okay? According to X. So X is the probability distribution. According to X, you choose K. You look at the expectation with respect to X of the regret. This is a regret, this is a vector, and then you make the scalar product with X. And this is 0. And it's clear, because the expectation here is the sum of xk, rk. And remember that the regret is the vector minus the component you are choosing. Here you have sigma of uk u, sigma of xk is 1. And here you have sigma of xk uk, which is exactly xu. Okay? So what you get is that the expectation is given by this. And when you take the scalar product with x, you get xu minus xu, which is 0. Okay? So this is the property here. But now, I claim that it's exactly the fact that this scalar product here is negative. Actually, it will be 0. Because your choice will be basically this. If you have a point in RK, you look at this positive part, and you define Xz to be proportional to Z. So remember, you want to be in this negative orthant. Okay? So if you start from a point here, you do whatever you want. Otherwise, you look at the positive part. So basically, you look at the projection. Okay? And then, given a projection, so this is a vector that has all components that are positive, you normalize it, and this gives you a probability distribution, and this is your strategy. So if the regret, so you take a probability which is proportional basically to the regret. You look at the average regret up to now, okay? If there is no average regret, if it's negative, you are fine. Otherwise, you look at the worst case and you take a probability distribution which is basically proportional to this. And then when you look at this property that you want, you start from this. This is the projection. This is the expected payoff. This is the projection. You want this to be negative. Actually, it's 0. Why? Because the projection is Z minus. You have this decomposition here. So when you look at when you have this decomposition, you know that this Z plus and Z minus are orthogonal. So there is one part here which disappeared, Z plus and this. So it remains to see G against this. But this is your choice. You remember, you normalize. So you have G, Z plus. Z plus is your choice. So this is the expected payoff. So it's exactly what I was doing. X is your chart strategy. G is your expected regret. So I have the expected regret times X, and this is 0. This was the previous lemma. So you have exactly this geometric property. What is needed for Blackwell is to have less or equal to 0, but here I have 0, so it's satisfied. So Blackwell condition is satisfied, so the set is approachable. So all the components will be eventually negative, so you have no regret. That's it. So this is the use of approachability to get a no-regret condition. Okay? I was doing this because it's exactly the same for the internal regret. In fact, it cannot be exactly the same because I was saying here I am working in RK, and I said, well, this vector has all positive components. I can normalize it, and I get the probability distribution. So I have a mixed strategy. It cannot be the case for internal regret because I am in RK square. Remember, I have a matrix here. Okay? So even if I have all components that are positive, if I normalize, I will have a matrix, and it's not a strategy. So the idea here is, given a matrix with non-negative coefficient, you look at the set of invariant measures. Okay, so the invariant measure for a positive matrix are the measure mu that satisfies this. Then what plays the role of the average property is this. Again, I start with K. This is a matrix, okay? I look at some invariant measure for this matrix. I take I take the K according to mu, okay? And I look at the scalar product with A. So mu is a set of invariant matrix with A. U is any vector. I choose a component K at random. This gives me a matrix of internal regret, and I look at the expectation here. And here I get 0. It's the same property than before. So now I look at the average internal regret. It's a matrix. I look at the projection. This will be a matrix with positive coefficient. I look at some invariant measure, mu. I choose K according to this invariant measure, and I have this property. And again, I use Blackwell condition. Okay? So geometrically, it's the same idea. Okay? It's the same proof to get internal regret or external regret. For internal, it's a bit more complex. Now, in terms of computation, it's quite different because in one case you have to compute some invariant distribution for positive matrix, while in the other case you have just, so this is a proof. For the other case, you have just to normalize. Okay, so that's it. So this is it, okay? So you know now that there are a procedure that satisfies either external regret or internal regret. So the application to finite game is basically for each player. So you have a finite set of players, and for each player, K will be his set of choice, and U is his payoff, but generated by the choice of the other. Okay? Every day, everybody is playing. You take your component, the others are playing something, and the sequence of vector U is your sequence of vector payoff. Okay? The first component of U1 is your payoff if you were choosing strategy 1, second component if you were choosing strategy 2, but the vector U are generated by the choice of the other, and you don't know anything about the other. Okay? So the no regret property here is some property of for one player, okay, facing other players and looking at his set of vector payoff. Okay? So here you see, we look at the procedure from the point of view of one player. Player 1 faces the online problem corresponding to the repeated game, where at each stage, if you have a profile of move, then the vector is his payoff, his choice, and this is the choice of the other. Okay? And he doesn't know. First, he chooses a choice, and then he observes. Okay? And the point is, what is the meaning of no regret here? And we will look at the situation for one player. So if one player is using a strategy satisfying no regret, but then the payoff will satisfy this, it's just the fact that everything is linear here. So the average of the payoff is the payoff of the average. And then you get this property. If player 1 follows some external consistency procedure, the empirical average distribution of moves will converge to this set. Okay? And if all the players satisfy some external consistency, it will converge to a point in the intersection of this set, and it's called the Anand set. What is more useful somehow, or well known, is internal regret and correlated equilibria. So if you use internal regret, it means that when you were using K, the day you were using K, it was better than using L. So this is the payoff if you were using K, and the other, it's using something else. And you know that it was always better when you were choosing K. K was better than any other choice. Okay? So it means that on the average, you reach an empirical distribution which is on this set. So this is the proposition. If player 1 follows some internal no-regret procedure, the empirical distribution of moves will be, or the accumulation point, will be in this set C1. Okay? If all players are satisfying some internal regret procedure, but without coordination, okay? So there are plenty of procedures satisfying no regret. I don't need any coordination between the players. It's just the property of the procedure. So if all the players are using procedures satisfying this property, then the empirical distribution of moves will be in the intersection of this set. And the intersection of this set is the set of correlated equilibrium distribution. So this is the link between unilateral procedure, no regret, and this concept of correlated equilibria due to Oman, which is the set of equilibria of the game where you add some signaling structure at the beginning. Okay? So the fact that there are procedures satisfying internal regret imply that there are correlated equilibria, and this is another proof of existence of point in this set, which is independent from Nash. Okay? Because the simplest proof of existence of correlated equilibrium distribution is to say that Nash equilibria are correlated equilibrium distribution, but here this is an algorithmic procedure showing that this set is non-empty. Okay? And this is the advantage of this approach. Okay? So this is part one. And this was the elementary approach, namely everything was discrete, the set was discrete, time was discrete, and you see the connection with games. Okay? Now you realize that, so this is the theorem. Okay? Now, no regret, part 2. Recall that no regret was this. You look at the average, you were choosing some component you had a payoff, and you compare to K. Okay? So this was your random payoff because you were choosing your component at random. Remember, in the Blackwell procedure, you look at the distribution, this gives you a probability, and you will choose a component at random. Now, I will subtract here the conditional expectation, okay? And I use the fact that the difference between the random variable and the conditional expectation is a bounded martingale. So the variation is controlled, and it goes to the exponential rate. Okay? So I will replace here the random outcome by the conditional expectation. Okay? So I replace this by this. Okay? So meaning that I get rid of the random effect here. I replace this random variable by the conditional expectation. Okay? So this gives you UK, and here it's xm, where xm is your probability at stage m. And I will look at condition where I have this. Okay? So the difference here is that I should get the difference between the random variable and the conditional expectation, but this is controlled by the previous Azuma inequality. Okay? So I will look at this, and now it's linear, so I can put any x here. I'm using x in the simplex of on a finite set, but you see that it doesn't play any role here anymore. So I can also, as well choose x in a convex set. And then I see that UM is on RK, but I can get rid of this. And the only point which is interesting is that you have a scalar product here. So the general formulation is now completely deterministic. You have a norm vector space, finite dimensional if you want for the computation, but you could work in a Hilbert space, or more generally, as soon as you have duality. The dual is V star, you have a duality map, you have a compact convex, and you have algorithm that associate to a trajectory of parameter in the dual, a trajectory of control. So you choose a control, okay, which is x, and then you observe u. And you choose x, and you observe u. So think of x being the probability, the law of your choice. In the previous case, you were choosing k. Now I said you choose x. X is the law of k. Okay, it's a probability law. Okay? Yes? U is in the dual. This is deterministic. Now the regret, I can go to continuous time. In discrete time, this is what you observe at stage m. You compare to a constant choice. This is your choice at stage m. In continuous time, you have this. Okay? So I go from discrete time and a finite space to continuous time and general duality. But the notion of regret is the same. Clear for everyone? Okay? You compare your choice to a constant choice. And the trajectory can be in continuous time or in discrete time. And the procedure satisfies the no-regret property if RT is a small o of t in time, or Rn is a small o of n. Okay? Clear? In the first case, everything was discrete, the set and the time. Here you are working with deterministic. It's no random anymore, okay? And it can be. And there are... so we will compare the performance in algorithm. And so there are 3 levels. A general case, UT is a bounded measurable process. So you don't know what it is, okay? It's coming, it's whether in continuous time or in discrete time with several components. It's in the dual space. And you choose S, and what you get is the scalar product. Second point, the closed form. What you observe is a function of what you choose. Okay? And this will be used in the class of games, because in games, what you observe is your payoff, which is a function of your choice, but also of the choice of the others. Okay? And the basic connection with convex analysis will be the gradient, where you don't know the function f, you choose xt, and what you observe is minus the gradient of the function at the point you were choosing. Okay? So u is a function of your choice. Okay? So this is a special class of this, and this is a special class of this. So you have three levels. General case, closed form, convex gradient. Okay? General case, this is online learning. One player facing something. Okay? You are facing the world, you don't know anything, and you try to predict or to adjust to some random event. Point 2, this will be the framework of game or closed form. And point 3, it's a convex gradient. You are looking at the gradient of a convex function, and you want to find the minimum of the convex function without knowing the function, and just observing the gradient at point that you are choosing. It's clear for everyone? Ça va? And then we'll see three different procedures that will have this property of no regret: projected dynamics, mirror descent, dual averaging. Okay? And just to summarize, this is standard. This will go to the Hilbert case. These two are more sophisticated because they adjust to the geometry of the problem in terms of norm. Okay? While this is basically Hilbertian or the standard Euclidean norm. Okay? And what is amazing is that you don't get, in general, more precise result here in this case than in the general case. Okay? So if you don't have more information on the convex function in terms of procedure and speed of convergence, you are not able to do better than in the general case of a process which is bounded measurable. Okay? Yes? And when I said you need more, you need something like Lipschitz gradient, which is a strong hypothesis on the convex function. Okay? And this is quite amazing. Point 1. Point 2, it's very simple. Namely, the idea and the proof are very simple. Okay? Now, but it's after 20 or 30 or 40 years of work. Okay? And now we can rewrite the proof. Okay. And what is extremely interesting also is that you look at the proof that were done in this framework by people working in convex analysis. And you realize that a lot of proofs do not use the fact that you are working with gradient. Okay? Yes? So you forget about the gradient, and then you realize that you don't look at proof where u is a function of xt, and you use the same proof and you get to the general case. But basically, it's the same tools. Okay? And this is really amazing. Okay? So the tools that were constructed, and their names, okay, and you have to go to the very beginning, like people like Mark Teboul or Freddy Oslander and so on. So they were working in like 50 years ago, 40 years ago, but in the framework of convex analysis, and they had all these ideas. And now you have people working on online procedure, and they say, well, look at my algorithm, and it goes very fast, and so on and so forth. And in fact, it's exactly the same idea, but they don't look at this paper were written 50 years ago in convex analysis, because they say, well, we are working in the general case, but in terms of idea, it's exactly the same. Okay? And this is what I wanted to explain very briefly. I try to approach 5. So framework 1, usual model of online learning. You observe a sequence or a family or a trajectory in the dual space, and then you adjust. And the 2 correspond more specific case where the parameter is a function of the adjust. Framework 2 is closed form, is relevant for games and variational inequalities. So basically, when you have Nash equilibria that can be written in this way, or variational inequality, it means that you will observe this, which is a function of x, and you want to find x that satisfies this. Okay, so in the term of game, it means that you are evaluation function. And, well, the examples are standard, and we'll consider, okay? So what you can think is if you have n players playing together and all the players are playing online algorithm, then the overall process, so for every player I, he will have this property, and he is controlling the I component. So what he observes is a function of his own choice and the choice of the others. It's like in a game, as usual. The outcome is a function of your choice and the choice of the other. And your choice satisfies this property. Okay? But if you look at the average, at the, the global vector here, okay, obviously it will satisfy the property because it's a sum of this. Okay? So the advantage of having this is it's decentralized, meaning that each player knows only his payoff function or his evaluation function, okay, and his sequence of moves. And you look at what will be the consequence for the collectivity or the group of players if all the players are using this. But they don't have the same information, and they don't play the same way, and they don't know that the others are using this algorithm. So it's strongly decentralized, okay, in terms of information and in terms of choice, okay? But if you have this property for each player, then you have this global property. So this is what is interesting in this area of online learning, because it's a collection of unilateral procedure, meaning that even if the others are not following no-regret procedure, you have some guarantee. You can say something about what you get, okay? In addition, if the others are playing no-regret, and framework 3 is a case of convex optimization. So convex optimization, basic algorithm, it goes back to Polyak, Nemirovsky, Nesterov, and so on and so forth. Okay, so this is a kind of book. So you see, compared to the part 1, all this is deterministic. Okay, there is no randomness. Okay, and it's a general case. It's not finitely. In the first case, the set K was finite. Here, you are basically working in a convex set. Okay, and it can be a continuous time or discrete time. But mainly, it's discrete time. Okay, so it's algorithm and convex analysis. Similarly, you have results in operation research and so on. And what is amazing is that you have the same tools, but with different names and different point of view and so on. I cannot elaborate on this, but I'll go. So basic property of the closed form, okay. What is amazing is you look at the solution of this. Variational inequalities here, okay? And when you have a C1 convex function, it means exactly that you are looking at minima. Okay, so there are two properties of this function phi, which is interesting, which is dissipative, being monotone or dissipative and being a gradient. And these are a class of process U for which you have well-known properties. Okay, so this is the external property. So this is, I will skip this because I will not have time to develop this. I will skip the potential. And I will give the result in case of closed form. Okay? So I assume that the procedure satisfies the no-regret property. Okay? Namely that RT of y is a little o of t, where RT of y is that. So you choose x. This is the vector u, which is closed form. It's a function of your choice. And for every y, this, you have this property. Okay? So first of all, if this phi is continuous and the trajectory converge, then it will converge to a solution of the variational inequalities. And it's clear, because you have this, is if this converges to a point, and this is continuous, then RT divided by T will converge. This will converge to phi of x, and you have y of x, okay? And this will be negative okay, because it's smaller than 0 when you divide by t. So you have this smaller than 0 for every t, which is imply that x satisfies this inequality. So in particular, it means that if it converges to an equilibria, or a solution of the variational inequality. Okay? In particular, if it's a stationary point, then it's a solution of the variational inequality. And the point 2 is if you look at the time average, so time average in continuous time or time average in discrete time, and if phi is dissipative, so it means that it's anti-monotonic, then the accumulation point of the average will be a solution. Okay, so here it's very interesting. You look at the average regret, so it's 1/80. This is the regret. And you see that as a function of x, it's a mess because you have phi of x here and x here, and you have a scalar product. But what the monotonicity, if it's dissipative, says is that this is greater than this. And this is a miracle because there is no x anymore here and only here. So now it's linear in x. Okay, this is a constant with respect to x. So the t goes r. Here you have xt bar, xs bar, because you can take the average here. Okay, and when you look at accumulation point, this remains less or equal than 0. So what you get is that any accumulation point x hat of the average, but not of the sequence, of the average, will have this property. So this implies in particular that there are solutions. Okay, so the fact that there are no regret procedure implies that for every phi which is dissipative, there are solutions of the variational inequality. If you look at the specific class of zero-sum games, where the payoff function is C1 and concave convex, this is the proof of the min-max theorem. Okay? Since the procedure, there are procedures satisfying no regret, everything is bounded here. You have accumulation point. Every accumulation point will be a solution of the variational inequality. When you look at the variational inequality coming from a C1 game, you get the existence of, you get the min-max theorem. Okay, so this is a variant of a proof of the min-max theorem through accumulation point of algorithm. But it's more general, okay, because it's enough to have dissipative, and for example, there is a class of games described by Rosen, where you want uniqueness of Nash equilibria, so you want that there are some connection between the gradient, and the connection between the gradient is this, basically this dissipative property. Okay, so this is general property. Each time you have this, okay, in continuous time. And then for the convex gradient, it implies that, you remember U is minus the gradient. You use the basic gradient inequality. Okay? So when you take the integral, here you have minus, U is minus the gradient. You get this property. This is a regret. The regret is greater than this. You use Jensen inequality. It gives you that f evaluated at the gradient is smaller than y plus something which is negative. This goes to 0. So f of xt is smaller asymptotically than f of y. This is true for every y. So the accumulation point of the average are the minima of f. So it implies that for a convex function, without knowing anything about the function, you get a sequence that will converge to a minimum of the function, okay? Which is this property. Okay? So these are the example of results that you can do. And then you have continuous time property. So in continuous time property are like dynamical systems. Mathematically, they are simpler to analyze, but in terms of computation, you need for computer, okay, discrete time. So it's nice to look at the continuous or the dynamical system, and then there is some work to look at the connection between the continuous time and discrete time. But continuous time, yes. So I call a level function a function p that satisfies this. Okay? So you look at ut, xt is adapted to ut, and I say that p is a level function for this class ut xt if you have this property. Ut xt minus 1 is greater than the derivative of p of ty. P is positive, and it has this property. So if there is a level function, then you have the regret property, which is trivial because the regret is this, which is the integral here. This is the derivative, so this is p of 0 minus p of t. P is positive, so it's bounded, so it's p of 0, you divide by t, and it goes to 0. So you have the regret property, and you have also this property. So if there is a level function, you know that the continuous time procedure will work. And the three classes that I will describe, namely Euclidean gradient, mirror descent, and dual average, will have a level function. So it gives you immediately the fact that the no-regret property is satisfied in continuous time. Then to get it in discrete time, you have to mimic. So you have to make a nice discretization, and here it's difficult because the step size will play a crucial role. Okay, you cannot take any step size. The fact that the continuous dynamics of the property doesn't tell you anything about the discrete, because the discretization has to be adjusted to some property of the function here, but it gives you some idea of what kind of Lyapunov function will be useful. Okay, so I will basically end by this. Okay, I will skip this. Hilbertian project. So class 1, projector dynamic. So this is the scalar product. This is the UM. This is the new, and this is the previous one. So you start, this was your choice at stage M. You change your choice at say M plus 1 is a function of what you observe. Okay? So it's basically, you want to go in this direction, but you have to take count of the previous one. This is in discrete time. And this is the formalization in discrete time. You project over R, xm plus 1, so it's basically a gradient dynamics, okay? And this is the step size, okay? The variational characterization is this. If you divide by eta m, you have the continuous time analog. So what is the continuous time analog? It's this, okay? So ut minus xt dot, this is the process you generate. This is what you observe. And the property you want is that u minus x dot t times y minus xt has to be less than 0, which is derivative is the projection on the tangent space at x at the point xt of what you observe. Okay? And when this, so this is the dynamic in continuous time, and then you have a level function. This is a level function. Okay? What you want to prove is that this scalar product is smaller than this, and it's trivial. Okay? So you know that there is convergence, you know that there is no regret, and so on. And then you go to the discrete time. I skip here, you have trajectory and so on, continue discrete time version. Mirror descent. Here you assume that there is a function h, strongly convex for some norm. You look at the Bregman distance associated, and you look at the dynamics. The dynamics is like before, except that you replace here the norm by the Bregman distance. This was your previous choice. This is the new one, x. Minimizing here, and altogether, you get x plus 1. The variational formulation is this. You divide by eta m, you let eta m goes to 0, and this is the continuous formulation. So it's the same than before, except that now you have the, the derivative of the Bregman divergence at xt. Okay? And the previous case corresponds to ht, which is 1/2 of the norm. Okay? And then you see that if you derive the Bregman distance, you have this property, which implies that the Bregman divergence of h is a level function. So you use the first case. If you have a level function, then there is convergence, and you have no regret. Same proof. Then there is the discrete time version, which is more difficult. And third case, dual averaging. Here you have a perturbation function, which is small a, lower semi-continuous and so on, strongly convex. The dual averaging, this was introduced by Nesterov. Here it's different, because in the previous case, what you do at stage m plus 1 is a function of what you were doing at stage m and the new observation. Here, what you are doing at stage m plus 1 is just a function of the sequence of observation. So it's cumulative. In the first case, it was adaptative. So xm plus 1 is just a function of what you observe up to now. And then there is a perturbation here. Again, you can look at the functional conjugate, and you have this expression here. So in continuous time, you get this expression here. Xt is just the gradient that the functional conjugate of your perturbation function evaluated on the cumulative point. Okay? And what will play the role of the level function is the Fenchel coupling. So Fenchel coupling is this. You prove that you have this property, which proves that W is a level function. So again, you know that there is a no-regret property and convergence in 1/t. And then there is some work to go to the discrete case and so on and so forth. Okay? So I will basically stop here, except that I would like to say that what is amazing, the replicator dynamics, has nothing to do. This was introduced by biologists who were looking at the reproduction of one population with different types. Okay? And the parameter is the fitness, namely the average number of outspring you get. Okay? If you put A against J, there are several genes, then this is the payoff of A. Okay? And you look how the frequency of types evolve in the population. You have this. Then you go to 2 population, then you go to n population, and then you go to one guy facing some process. So it's the unilateral approach. Okay? And then you get this process here. Okay? And what is amazing here is that there is a connection with first the logit map, and then with the exponential weight algorithm in continuous time. And finally, what you observe is that there is connection between the replicator dynamics and the dynamics I was introducing here, and I get basically this. The incremental differential approach, which corresponds to mirror descent, this corresponds to the incremental replicator dynamics, and the cumulative approach corresponds to the logging approach, which is the logging way of looking at the replicator dynamics. So you see that coming from completely different approach, you get the same kind of dynamics, and this is really fascinating. And I stop here.
Thank you.